Good morning, everyone. It's Miss Maneely, and I am going to go ahead and go through the lesson on sampling distributions for the sample proportion. So we're dealing with the distribution of a bunch of p-hats. Before we get started, let's go ahead over the warm-up. In each of these first examples, you're asked to identify the underlying number as either a parameter or a statistic, and then use the appropriate notation to describe each number. So in letter A, it says a 1993 survey conducted by the Richmond Times-Dispatch 1 week before Election Day asked voters for which candidate they would vote for the state's Attorney General. 37% of the respondents said that they would vote for the Democratic candidate, but on Election Day, 41% actually voted for the Democratic candidate. So remember, the population parameter is referring to everybody, and that's going to be our P. So we're dealing with a proportion in this case. I think it's obvious because of the percentage, but that's usually the very first thing you want to consider. Am I dealing with a mean or a proportion? And in this case, I'm looking at the proportion of people who would vote for the candidate. So the population parameter, and I'm just going to reinforce that that's the population parameter, P, is going to be what actually happened, the vote that actually occurred. And so that's going to be the 41%. The sample statistic is going to refer to our p hat, and that's what the result of the sample or the respondents to the survey, and that's going to be the 37%. Okay, in the second example, the National Center for Health Statistics reports that the mean systolic blood pressure for males 35 to 44 years of age is 128 and the standard deviation is 15. The medical director of a large company looks at the medical records for 72 executives in this age group and finds that the mean systolic blood pressure for these executives is 126.07. I think it's pretty obvious in this case that we're dealing with a mean and a standard deviation. So the parameters in this case, the population parameters, and maybe I should spell out that it's the parameters versus the sample statistics. And we want to make sure that we're differentiating this time, because in the first problem we were looking at proportions, and so we're using the notation of p and p hat. When we're dealing with means, we want to make sure we refer to the mu and x bar. We're also given a standard deviation in this case. So again, the National Center of Health Statistics reports that the mean for all men is this 128 and the standard deviation is 15. Those are my population parameters. So this is going to be the 128, and with means you do want to make sure that you include units, and I'm assuming that in this case, let's just go ahead and say blood pressure. I'm not sure how it's measured, but we do want to remember that when we're dealing with mean and standard deviation, we should use context. And the standard deviation in this case is, again, 15. So that was given to us. And then we have medical records of 72 executives. That 72 corresponds to our sample size. So I would actually use N to describe that. And in this case, the sample mean is 126.07, and whatever blood pressure is measured in. So I'll just say blood pressure. Okay. In number 2, you're asked to create a graph. So it says, suppose two different statistics, let's call them statistic A and statistic B, can be used to estimate the same population parameter. Statistics A has low bias or lower bias than B, but it also has higher variability compared to B. On the two axes below, draw two parallel dot plots showing 8 values of each statistic that are consistent with these characteristics. So remember, with bias, we're talking about whether or not the center of our sampling distribution matches the center of the population. And if it's not on target, then we say that there's high bias. So if A has lower bias than B, the center of my distribution is going to match the center of the population. If B has higher bias, then that means that the center of its distribution is going to be off center. So if this is the mean of the population, or let's just call it the population parameter, I'm going to end up drawing 8 dots. And so I've gotten 3 for each so far. I also know that A has high variability. So with A, I want to make sure that my dots are really spread out. So I have 5 more dots to give. I'm going to go ahead and put 1 more here, and then I'm going to evenly spread the rest of them out. So there's my 8 dots. They're really spread out. When I'm dealing with the second one, it's got high bias, but it's going to have low variability. So I'm going to go ahead and put my 4 dots here and then 2 dots on either side that are really close. And obviously, there's an infinite number of ways that you can draw these graphs, but you want to make sure that A has a center around that arrow and B is off center. And then for A, you want to make sure that the dots are really spread out, whereas in B, they're going to be pretty close together. Okay. In the last one, it says a large pet store that specializes in tropical fish has several thousand guppies. The store claims that the guppies have a mean length of 5 centimeters and a standard deviation of 0.5 centimeters. You come to the store and buy 10 randomly selected guppies and find that the mean length of your group is only 4.8. This makes you suspect that the mean fish length is not what the store says it is. To explore this further, you assume that the length of the guppies is normally distributed and you use a computer to simulate 200 samples of 10 guppies from the store's claimed population. And below is a dot plot of the means from those 200 samples. So this is similar to the simulation that I showed you, that website that I went to where we could gather a bunch of different samples. That's essentially what this graph is showing you. So in letter A, it says, what is the population in this situation, and what would be the parameters, or in what population parameters have we been given? So the population in this case would be all of the guppies in the store. And then the parameters that were given, if we assume that they're true, is that the mean length is 5 centimeters and the standard deviation is 0.5. So we're given this 5 centimeters and then sigma. And notice that I'm using the Greek letter for sigma to represent the population. If it was from the sample, I'd be using S. Okay. And then in letter B, it says the distribution of one sample is described in the beginning paragraph. What information have we been given about the sample? And all we know about the one sample is that we took a random sample. And that we know that the mean is 4.8. And so that's going to be an X bar value. And that's slightly lower than what we would expect it to be. And then in letter C, it says, is the dot plot above a sampling distribution? And it's an approximation of a sampling distribution, but it's not exactly a sampling distribution because it doesn't show every possible combination of 10 guppies from this store. It's just a simulation, so it doesn't include every possible sample. So it's close, it's an approximation, but not exactly. So it doesn't include every sample, which is what a true sampling distribution should be. And lastly, it says, do you think the store is being honest about the length of the guppies? So if I think about this guy got, his mean is only 4.8. So that's here. So I want to think about how extreme that is. Our total number of samples is 200. If I think about all the samples that are less than 4.8 and I count them up, see. I think I counted that to be, so basically what I'm looking at is the probability that my p-hat, that my sample value is less than or equal to 4.8. And we're going to do this notation a lot today and over the next couple of classes. And I counted 21 samples that are below that. Out of the 200, that ends up being about 10.5%. And that's not really that unusual. So if it's not unusual, I spelled unusual wrong. Let's try this again. Okay, so very often people make claims and then we look at our samples to see how close our value is to the claim. And when our values are different, that makes us suspicious about the claim. And so one of the things that we're going to do this semester is we're going to do we're going to be testing claims, and they're called tests of significance. And we're essentially trying to find the probability of seeing the sample that we saw or something more extreme, which is what we did in letter D. If I look at the probability of finding a proportion that's less than 4.8, and again, this is just a simulation, so it's not exact. So I'm actually going to put a little prime there where my probability is, because it's based on an experiment, not theory. But seeing a probability of like 10.5% really isn't that unusual. If the probability of my sample was less than 5%, then that's an indication that I shouldn't have seen it. It's probably not a coincidence, and therefore that would give me evidence to reject the claim. But since, it's not that unusual to get a sample that's less than 4.8 centimeters in terms of the length of these guppies, I really don't have any reason to suspect that the store owner is telling me or not being honest with me. Okay, so our result is not that unusual, so it doesn't give us enough evidence to be suspicious. Okay, so I'm going to ask at this time for the substitute to go ahead and pass out the classwork worksheet. And so today we're going to be looking specifically at sampling distributions for sample proportions. So we're going to be looking at what happens if we take a sample, determine the proportion of success in that sample, and then do that multiple times. So I'm going to essentially be looking at how a bunch of p-hats are distributed. If I were to continue to take samples over and over and over again, how are all my p-hats being distributed? And so we're going to look at at when this distribution is approximately normal. We'll be able to determine the mean and the standard deviation, and then we'll also be able to calculate probabilities for sample results. Okay, so let's get started with the notes. And just remember that everywhere you see this red star, this is something that's like really important in this chapter, and it's something that should get transferred to your study guide at some point so that you have all the important information in one place. So when we're looking at the sampling distribution of the sample proportion, we're no longer looking at the distribution of individual outcomes. Now I'm looking at a sample where I've looked at the number of successes and I've divided it by my sample size. So it's sort of like the binomial setting, except this time my random variable is not the count of successes. So remember, in a binomial setting, x represented the count or the number of successes. When we're dealing with p hat, we're going to talk in a minute about how p hat is distributed, but p hat represents the proportion of successes. And so you're going to see that the setting is very similar to the binomial setting, except the way we look at our random variable, it's no longer the count of successes. Now we're dividing by the sample size. And that's really important, because if I were just looking at the count, when I'm taking multiple samples, if I'm comparing the count and my sample sizes are different, or if I have like non-response in one sample and not another, then comparing the counts isn't really going to be fair. So I want to kind of take into consideration the number of people who responded. So looking at proportions is going to enable me to compare one sample to the next. The other thing you want to pay attention to is that if I'm dealing with a binomial distribution, the count of successes, this is a discrete random variable. Once I start looking at a proportion, now I'm looking at that fraction, which can be any decimal between 0 and 1. It becomes a continuous random variable. And so that's going to change. If I'm dealing with p hat, it's no longer a binomial distribution. In fact, if you take a look at the slide, it's going to be approximately normal. And so I need to figure out what the mean and the standard deviation are going to be for that normal distribution. And so if you take a look, so the shape of the sampling distribution for p hat is going to be approximately normal, and it's going to be closer and closer to a normal distribution for larger sample sizes. The mean of my sampling distribution, so even though I'm looking at a distribution of a bunch of p hats, a bunch of proportions, the center of this distribution, I can still take the average of all those p hats. So the average of all my p hats is going to be whatever the population proportion is. And so sometimes students get confused because now we're somehow merging means and proportions in one thing. So the mean of all my sample proportions should be equivalent to the population proportion, which is often unknown. Okay, so when I'm looking at my normal distribution, I can say p hat is distributed normally with a mean of p, and the standard deviation, I'm going to give you that formula in just a second. We already have talked about what happens with the variability. As n gets larger, my standard deviation is going to decrease. So the standard deviation is going to get smaller as our sample size increases. That is always going to be true no matter what kind of sampling distribution we take. As my sample gets larger, the amount of variability is going to decrease. The formula for the standard deviation, and notice that this is a different formula. It's not the same formula that we used with a binomial random variable, and that's because we're not dealing with the count of successes anymore. Now we're dealing with the proportion of successes. So the formula for my standard deviation is a little bit different. It's the square root of p times 1 minus p, or the probability of failure, divided by n. But here's the other thing. Remember how we said that when we're sampling without replacement, it's necessary that we have that independence. So in order to use the standard deviation formula, we have to check that the population is at least 10 times our sample size. You have to physically write this on your paper, and you're not going to be prompted to do it. So anytime you're using the standard deviation formula, you have to make sure that you check that the population is at least 10 times your sample size. Okay, so if we go back to that previous slide where I was talking about the distribution of p hat, the standard deviation now is going to be p times 1 minus p over n, and that whole quantity is underneath a square root. And so if you have a binomial setting and your sample is large enough, and we're actually going to talk about the condition for normality, it's the same as it was before. As long as your numbers of successes and failures are both greater than 10, p hat is going to be approximately normal. So let's take a look at an example. In number 1, it says you ask a simple random sample of 1,500 first-year college students whether they applied for admission to any other college. Well, there are over 1.7 million first-year college students, so the rule of thumb is easily satisfied. So in this case, my n value is 1,500. And if I check the population to make sure it's greater than or equal to 10 times n, well, 1.7 million looks like that. And 10 times my sample size is just going to be 15,000. And so obviously 1.7 million is greater than 15,000. In fact, 35% of all first-year students apply to colleges other than the one they are attending. What is the probability that your sample will give a result within 2 percentage points of the true value? So what would be the mean of p hat? We said in the formula that the mean of p hat is equivalent to the population proportion. So what's the population proportion? In this case, it's going to be that 35%. It's what we're given. So the mean of p hat, that's the sampling distribution mean, is going to be 0.35. And remember, when I'm dealing with proportions, I don't need units. If I want to calculate the standard deviation, I'm going to use my formula where we have the square root of p times 1 minus p over n, which is 1,500. And that ends up being 0.0123. Now remember, in order for me to use that formula, this condition has to be met, and so it's met. In letter C, it says, what's the probability that p is between 0.33 and 0.37? This is going to be a normal distribution calculation. Now, we need to talk about why it's normal, and that's actually coming up next. If you think back to what we did before with the normal approximation of the binomial, we said that it can be normal as long as n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. As long as both of those conditions are met, we can use a normal distribution to calculate the probability. And in this case, again, n is 1,500. My probability of success is 35%. And 35% of 1,500 is 525. So that's clearly greater than 10. And if I just subtract that from 1,500, that gives me my percent, or my number of failures. So that means that the number of failures is going to be 975. That's also greater than or equal to 10. So the normal condition is met. If I want to calculate this probability, and this 33 and 37, if you think about the true population proportion is 35%, and we're looking for 2 percentage points, or with our value within 2, so 2 less would be 33%, 2 more would be 35%. That's where this came from. So, of course, just like with any other normal calculation, we would want to standardize. So I need to figure out the z-score for 33%, so 0.33, minus the mean, which we said is 0.35, divided by my standard deviation. And that gives us a z-score of negative 1.626. Well, the other value, 0.37, is just 2 percentage points above my mean, and so that's just going to be a positive 1.63 or 626 because of the symmetry. Because remember, this is the center of my distribution. So if I'm looking at 2 values less than that and 2 values above that, their z-scores are just going to be opposite. And so then I can use my normal CDF. And it doesn't matter if you want to use the parameters for p hat or z, just be consistent. So if I want to use p hat, my lower bound is 33%, my upper bound is 37%. And notice that when you're dealing with p hat, you want to make sure you're entering everything as a decimal. My parameter for the mean is 35%, and the standard deviation is 0.0123. Yeah, you don't want to enter whole values. Okay, and so the probability of this occurring is going to be 0.896. Okay. All right, so let's take a look at the second rule of thumb. And again, we just kind of mentioned that. The accuracy of the normal approximation is going to improve as our sample size increases. And if you have a fixed sample size, the normal approximation is most accurate and appropriate when p is close to 0.5, and least accurate when our p is near 0 or 1. And that's because there's not going to be, your distribution will be more skewed. And so essentially, in order to use a normal distribution, we need to check that n times p, which is the number of successes, and n times 1 minus p, which would be your number of failures in your sample, are at least 10. And so this is the second rule of thumb that is required to use a normal distribution. Notice that there's a star next to it, so this should too go on your study guide. Okay, so essentially I'm going to walk you through a whole problem. And then there are a bunch of practice problems that I'm going to have you guys do together in class. So number 2 says, suppose that 21% of students in a certain school system earn a place on the honor roll. The proportion of students earning honor roll in a simple random sample of 1,500 students should therefore be close to 21%. It's unlikely to be exactly 21% because of sampling variability. If a sample from the school district contains only 19.2% of students who earned honor roll, should we suspect that the sampling procedure is somehow underrepresenting these honor roll students? So basically what it's saying is if the true proportion is 21%, and I take a sample and my sample statistic is only 19.2%, I can see that that value is lower. But is it low enough for me to suspect that something's wrong? And the two conclusions that I would draw if I think something's wrong is either that the claim about the population is wrong, or maybe I made a mistake in my calculations. And that's pretty much what this question is wondering. Like, is that 19.2 so low that it's screaming that there's a problem either with my procedure or with the claim? So let's find out. So we're going to basically determine the probability that a sample contains no more than 19.2%. So I'm looking for the probability that I would get a result as extreme as this. And because the value is less than what I expected it to be, I'm essentially trying to find the probability of obtaining a sample proportion that is less than 0.192. That is as extreme or more extreme than the one I got. So in order to calculate this probability, I'm going to have to check a few things. So I have to check the rule of thumb number 1, that the population is at least 10 times my sample size so that I can use the standard deviation formula. And so I don't really know how many students are in this school district because it doesn't tell me. I don't even know what the school district is. So this is an assumption that I'm going to make. I have to assume that the population is at least 10 times 1,500, which is my sample size. So I have to assume that there are at least 15,000 students in this school system. And I think that's probably a reasonable assumption. Okay, so we're going to assume that's true. Rule number two, or rule of thumb number two, is what I need to check in order for me to use a normal approximation. If I don't do that, then there's really no way for me to find the probability with this, because I need to know what kind of distribution to use to calculate the probability. So in order for it to be normal, I have to check my n times p, and so again, it's 1500 times 21%, and n times 1 minus p. And notice that I'm using the population parameter, not the sample statistic. We will, in some cases, use a sample statistic, but that's only when we start getting into confidence intervals. So for now, you're going to use the population parameter. My probability of failure is going to be 79%. And so when I check, I'm going to have 315 successes. That's obviously greater than or equal to 10. And I'm going to have 1,185 failures, which is obviously greater than or equal to 10. So since this is true, I can say p hat is approximately normal. Okay? The next thing it's going to ask you to do is to calculate the mean and the standard deviation for p hat. And remember, we said the mean of p hat is simply equivalent to the population parameter, which we were told is 21%. The standard deviation for p hat is going to be my p, 0.21, times my probability of failure, which we said is 0.79, over my sample size, which is 1500. And when you calculate that, you get 0.011. And so basically, I'm going to say that p hat is approximately normal with a mean of 0.21 and a standard deviation of 0.011. So if I want to calculate the probability of my sample being less than or equal to 19.2%, I'm going to standardize it. So I'm going to take my 0.192 and subtract my 0.21 and divide by my standard deviation. And we get a z-score of negative 1.636. And then I'm going to go ahead to my normal CDF, because again, remember, we're using CDF because this is a continuous distribution. My lower bound, I don't know. It's negative infinity, so that's where I'm going to go ahead and type in a bunch of negative 9s. And then again, it's up to you if you want to use the distribution of p hat or z. I'll go ahead and use z this time. So I'm going to type in a negative 1.636. And since I'm using z, the mean of that distribution is 0, and the standard deviation is 1. And so the probability is 0.051, essentially. So if you think about that, this value is pretty low. It's really unusual for me to see a sample result so low. It's only going to occur about 5% of the time. And we usually draw a line around 5%, and if we set the value ahead of time, then it is a hard line. But in this case, just for the sake of argument, since the sample result is so unusual, it shouldn't have occurred. Well, it likely did not occur by chance. How about if I put it that way? And basically what I'd say here is the p-value. And those of you that have taken AP Psych, the p-value is referring to this probability. Okay, so since the sample result is so unusual, it likely did not occur by chance. And this leads us to conclude that something's wrong. It could be that the claim is too high. or there's an error somewhere in our methods. And so I think the original question suggested, is it possible that our sampling procedure somehow underrepresented the honor roll students? So if it is true that 21% of students in the school system made honor roll, and I got a result that was so much less, that's probably an indication that perhaps my sampling procedure was biased, and perhaps I underrepresented the honor roll students in my sample. They were somehow underrepresented. So when you get a result that's really, really unusual, that's a red flag. That tells you either the claim is wrong, or I shouldn't say it's wrong. That gives you evidence against the claim, or it leads you to conclude that perhaps something was wrong in your procedure. Okay, so at this point there are, I believe, 3 more problems that are similar to this, and I would like you to go ahead and work with the people around you to complete them in class. I am going to have the answers available for you in a few minutes, but at this time I'd like you to just press pause, and for the next 20 or so minutes I'd like you to complete those 3 problems, and then at the end of the period, if the sub could just press play again and show the results to the class so that you guys can check your work, I'd appreciate it. It's like one last thing. On your study guide at this point, you should have that last column of the table completed, where it talks about the distribution of sample means, the shape. If n is large, the shape should be bell-shaped and symmetric. In terms of the center, the mean of your sampling distribution is going to be the population proportion. And actually, let me make this bigger for you so you can see. Okay, maybe you can see that a little bit better. So if n is large, the shape is going to be bell-shaped and symmetric. The center of your sampling distribution, so the mean of p hat, should be your population parameter, your population proportion, p. Your spread, that's your standard deviation, should be equivalent to the square root of p times 1 minus p over n. But again, you can only use that formula if you verified that the population is at least 10 times your sample size. And if you can't verify it, then it's an assumption that you can make. And it's often an assumption that you can make safely. In order to use a normal distribution, you must check that condition, that n times p and n times 1 minus p are both greater than or equal to 10. So don't call it normal if you haven't done those calculations. If it asks you to describe the shape and you've got a really small sample, you want to make sure that you're just referring to it as bell-shaped and symmetric and not normal unless both your successes and failures are greater than 10. Okay, so now I mean it. You've got 3 practice problems. I'd like you to go ahead and pause the video at this time, and in about 20 minutes when everybody's done, I'd like you to go ahead and play so I can show you the correct answers. Okay, I hope everybody's had a chance to complete these 3 problems. So in number 1, you're asked whether or not it's appropriate to model the distribution of the sample proportions using a normal probability function. So in the first one, the teacher tells the statistics class to run a trial in a simulation that consists of tossing a coin 10 times and determining the proportion of heads. So in this case, our n value is 10, and we know that the proportion of heads, the true population proportion, should be 0.5. Well, if I take a look at n times p and n times 1 minus p, both of those values are too small because both of them have to be more than 10. So I really didn't even have to do those calculations. In order for me to be able to do a normal distribution, the sample size has to be at least 20 so that I can have 10 successes and 10 failures. So it's not appropriate to model this particular scenario with a normal distribution because our sample size is too small. We could try to do it with a binomial distribution if we wanted to, but we couldn't use a normal approximation. But instead, if we take a look at letter B, if we toss the coin 50 times, now when I multiply n times p and n times 1 minus p, both my successes and failures are greater than 10, and so a normal approximation would be appropriate. So I could use a normal distribution to calculate probabilities for this problem. In the second one, it says, based on past experience, a bank manager believes that 7% of people who receive loans are not going to make payments on time, and the bank has recently approved 200 loans. So if we define the variable p hat, that would be, and remember, just like with any other variable, you always want to define your variable. So if I define my variable p hat to be the proportion who do not pay on time or who pay late, I know from the problem that my true population proportion is 7%, and that the N in this case are the 200 applications that have just been approved. And so the mean and the standard deviation, the mean for my sampling distribution is just going to be the true proportion of the population, which is 7%. And to calculate my standard deviation, I just use the formula, and that's 1.8%. But remember, in order to use that formula, I have to check to make sure that the population is at least 10 times my sample size. And I don't know the number of applications, so it's an assumption that I'm making. In letter B, we need to check for normality. So this is where I check my successes and failures, and in both cases, they're greater than 10. So I can say that p hat is distributed normally with a mean of 0.07 and a standard deviation of 0.018. And if I want to know the probability that over 10% of clients will not pay on time, I'm looking for the probability that p hat is greater than 0.1. I'm going to standardize it the way I always have, and then use my normal CDF to calculate the probability. In the last one, you're not given any prompts. But you still have to do all that work. And in this case, the one thing I did forget to do was define my variable. In this case, p hat is going to represent the proportion of seeds who germinate. So don't forget to do that. Okay, so I'm given in the problem that 92% of the population, that's the germination rate, and I've got a sample of 160 seeds. So before I can do any of this, I have to do all this legwork. I have to check both of those conditions, that the population of seeds is at least 1,600. I don't know how many seeds there are, but I'm guessing it's probably more than 1,600, so that's a safe assumption to make. I have to check my successes and failures, and in both cases, they're greater than 10. So therefore, I can say that p hat is approximately normal. So these two conditions tell me it's normal. This assumption allows me to use the standard deviation formula. And once I have those values, I can continue and proceed with the normal distribution the way we have all year. All right, so at this time, I would like you to complete an exit ticket. This is to be done independently, so there should be absolutely no talking. The exit ticket will be submitted at the end of the period, so please make sure your name is on it, that you've shown all work. You may use your notes on the whole thing. You can use your study guide, you can use the textbook if you want, but you cannot use each other. If you happen to finish your exit ticket before the bell, then use the rest of the remaining class period to complete your homework. So at this time, if the substitute could pass out the exit ticket, and then while you're working on the exit ticket, if he could also pass out the homework, there should be no talking at this time. Thanks, guys, and I will see you next class.